So now let's talk about how we can actually use logarithms to find solutions. The first one is what we talked about before in the first video. A value a is equal to 10 raised to the power of log a. For example, 50 is equal to 10 raised to the power of log 50. So if I go to my calculator and put in log 50, I get this approximate exponent value. So 10 raised to this number here is approximately going to give me 50. Same as if I go 736. This is then equal to 10 raised to the power of log 736. So again, I put log 736 into my calculator and I get this exponent here. So 10 raised to this value is going to give me 736. The next one is the idea that a, any base a, raised to the power of x is equal to x times the log of that base. So for example, here I have 10 raised to the value of x is equal to 80. So I take the log of both sides, the logarithm. Using this law up here, this side becomes 10, so x log 10 is equal to log of 80. But the log of 10 with base 10 is just 1, because 10 raised to the power of 1 is simply just 10. So that means this part here just goes away. So x is equal to log of 80. Or in this case, this value here, x, so we started, is equal to 1.90309 approximately. So all we're saying here is we're trying to say that the exponent times the log of the base is equal to the log of whatever we're trying to find. Okay, here we have some value base a raised to the power of x, and this is equal to another constant value called b. So here I might have 10, that's equal to 10 raised to the power of log a raised to the power of x, and this is equal to 10 raised to the power of log b. Just using our basic exponent laws, we see that the bases on both sides of our equation are now the same. So we can ignore the bases and just look at the exponents, meaning that x times log a is equal to log b. Divide both sides through, and what I get is that this value here, x, is equal to the log of b divided by the log of a. Give you an example. So here I have 3 raised to the power of x is equal to 47. So I'm trying to find a value of x that I can raise 3 to give me 47. Applying this rule. So applying the log laws, 3x can be written as 10 raised to the power of log 3, all raised to the power of x. And this is equal to 10 raised to the log of 47. Again, the exponents are, so the bases are the same. So all we have to do now is look at the exponents. So then I get x times log 3 is equal to log 47. So that means the value of x is going to be log 47 divided by log 3. We simply enter this into our calculator and we get a value here that x is approximately equal to 3.50456. So again, if we took this value of x, put it into here, 3 raised to this power, we would approximately get a value of 47, as we see here. This is more exact value, but again, very, very close. Okay, let's try a more complex example. Here, what I have is the value of 297.4 is equal to 6.5 times 3 raised to the power of 0.29x. Looks complicated, but again, it's exactly the same as we've been doing. So first of all, what I would do is I would divide both of these sides by 6.5 so that I get the exponential part by itself. So once we divide everything through, 6.5 divided by 6.5 equals 1. So now, over here what I have is 45.754 is equal to 3 raised to the power of 0.29x. Now I can apply my log rules. So, then, that means 10 raised to the power of log 45.754 is equal to 10 raised to the power of log 3, all raised to the power of 0.29x. See? There's the log, so there is the higher power. So again, what we have is the exponent, the bases are the same. We have bases here of 10, so all we have to do is look at the exponents, which I have up here. So, log of 45.754 is equal to log 3 multiplied by 0.29x. Now, I divide through both sides by a value of log 3. So over here, log 3 divided by log 3 is 1. So all I'm left with this part now is 0.29x divided by log of 45.754 divided by log 3. So this whole thing now comes out to 0.29x is approximately equal to a value of 3.48. Divide both sides by 0.29, then of course this comes down to x, and I get a value that x is approximately equal to 12. I'm not sure the specific value here. So what that means is, back to what we were saying, if we put a value of 12 here for this value of x, we would approximately get this value here of 297.4. I know there's a lot going on here, and I know I keep saying the word log again and again and again. But like I said, all we're really doing is rearranging our exponential equation or our exponential expression so we get the same base and looking at our log values. And remember, all log is a specific exponent value which we can raise a specific base to, in our case 10, to get a specific answer.